Hello, and thank you for joining my presentation. In this talk, I'll be presenting our recent work on ice detection and monitoring in a wireless and pervasive way using battery-free RFID sensors enabled by complex impedance dipole antennas. Before we go into the details of our approach, ice detection and the buildup of ice more generally in smart cities, in industrial application, even in environmental monitoring, is an ongoing challenge that has been tackled in many ways. There are lots of statistics on billions of losses due to freezing pipeworks and also workplace injuries in places like the UK and the US. And at the moment, all the industry approved ways of monitoring ice are very manual and relying on visual methods. And even when we look in scientific literature, near-infrared cameras and optic fibers are also available. However, they cover small areas, they're expensive, and they require complex computation and also complex sampling circuitry. RF sensing and RFID sensing has been applied to almost everything. However, there are lots of references which describe ice as being almost transparent to microwaves due to its very low dielectric properties. However, looking in recent literature, we found that a very high quality factor microwave resonator has been used as a sensor for detecting ice in real time. And in our recent work published in the IEEE Census Journal, we have extended this approach and demonstrated the same can be done in a very low cost way and using RFID tags. You can find more about these background, more about the statistic in the introduction of our paper in the IEEE Census Journal, which I'll also be covering in this presentation. So to summarize, RFID antennas, they are enabled of battery-free sensing because they are powered from the reader using radio frequency energy harvesting, and the gain changes in the antenna in response to an external stimulant or to a sensing material can be detected through the signal strength, or in other words, the RSSI, or the relative signal strength indicator. For a simple tag which has got a read range of 10 meters, which is widely reported in literature, a single reader, which is not too expensive, can cover an area of over 100 square meters, which is great for wireless ice sensing applications if you consider an application like wind turbines or the outdoors and train platforms, for example. The antennas can also be encapsulated for high mechanical reliability, which is something we have shown for wearables that could withstand temperature, washing, and also different stimulant up to industry standards. So let's first look at the antenna design. We're using an existing antenna design which we have proposed for RFID application. It's a compact, flexible antenna implemented on a flexible polyamide filament. It's very thin. It's got a profile narrower than 3 millimeters, and the antenna itself is very lightweight. Its thickness is less than 50 microns, and it's encapsulated using heat-formed captain or heat-formed polyamide to withstand washing, water, or any external rigor diffuse. You can see in the three-dimensional block diagram, you can see the antenna is covered by a layer of ice of thickness T, and you can see in the photograph of the antenna during our testing where it's completely covered in ice after being frozen. So let's look at what ice and loading with ice does to an antenna. Ice, as we have discussed, is almost transparent to microwaves. In other words, that means it has got a very low real permittivity, around 3, and also its tangent delta is extremely low. In fact, it's lower than 0.01, and that's lower than a lot of the high frequency circuit laminates, making it very low loss material and meaning that it will not degrade the antenna's performance. However, the permittivity, regardless of how small, when it gets into the near field of the antenna, it will act as superstrate, and any superstrate will shift the resonance of an antenna, and more specifically, a wire type antenna like an RFID dipole. So in the graphs, you can see the simulated and measured input impedances, with simulated being the dashed line and measurement being a solid line. And we can see that as the antenna is loaded, the input impedance and the resonance shifts from a frequency around over 1 gigahertz to a frequency below 900 megahertz, very close to 868 megahertz, which is the frequency at which we interrogate our RFID tags. You can see the photograph of our measurement setup. The antenna is measured using a differential balance jig using a 2-port VNA, and it's completely covered in ice while we're performing our measurement. You can see that the resonance shift happens to both the real and the imaginary impedance, and that the measured quality factor and the measured magnitude doesn't change significantly with the ice because it has got such a low tangent delta and it's a very low loss material. And as you can see, both the simulation and measurements are in fair agreement, showing that the ice has got a very predictable permittivity and it's very uniform. The model matches our practical measurements. What effect this has on the RFID tag is that the impedance matching of the tags near the 868 MHz EU RFID and license-free band improves. And when this impedance matching improves, it improves the realized gain of the tag, which then translates to a change in the gain of the antenna and in the RSS, which can be read by a simple low-cost RFID reader in any environment without requiring special hardware or special frequency bands. We can see here the measured results using a conventional RFID tag which we've designed, and you can see that for a distance from 1 to 10 meters, which is the full read range of the RFID tag, the RSS increases significantly when the antenna is loaded by ice, and the average sensitivity is in fact higher than 10 dB. The 10 dB, that's significantly higher than any noise which might be introduced in the system, which means that we can detect our response in a variety of environments, indoors, outdoors, with multipath reflection, and also with line of sight obstruction, whether that's by people or metals, which you can find a lot more about these experiments in our previous paper in the reference. What is more interesting to look at is the transition state between water and ice, and also during melting. Water has a significantly higher real permittivity compared to ice, and probably compared to the substrate of any antenna. It also has a very high imaginary permittivity in tangent delta, which means it will degrade the gain quite significantly. Recall that we are detecting the presence of ice through an increase in the signal strength and increase in the gain, so water will have pretty much the opposite effect. The gain will reduce, and it will mean the read range will also reduce. The tag at some point will stop being read. So there is no way based on this system that ice will be mistaken for water or mistaken for interference. If you look at the graphs which we have measured of the input impedance of the antenna, so we're performing these new measurements to see how the input impedance of the dipole changes in response to ice as well as in response to melting. As we've seen in my earlier slides, as you load the antenna with ice, the resonance shifts to a lower frequency, around 868, which is where we expect the antenna to operate. However, as this ice layer is left in room temperature and it starts melting, so if you look at 5, 7, and 8 minutes of melting, you can see that the amount of water increases, and even that small amount of water, which results in 5 minutes of melting, significantly shifts the resonance away from the operation frequency, and as a result, will reduce the realized gain significantly. So in a way, we can see that ice and water affect the gain in the opposite ways, even though both of them shift the frequency in the same direction, which is a lower frequency, and as we call it, what we call positive synthing, which I'll talk about more in my slides. Same can be observed for the imaginary impedance, where the resonance shifts to a lower frequency, and also we can see the changes in the magnitude, which are harder to predict and also highly dependent on the test setup, so we don't rely on them to detect any of the phenomena we're talking about. So let's look at the RFID performance and how it's affected by the melting of ice or ice thawing. And you can see that over time, as the ice melts, its RSS degrades. And that's directly because of the detuning and also because of the increase in the tangent delta, which reduces radiation efficiency and as a result, both the gain and the realized gain of our antenna. We can also see that the relative signal strength is thickness dependent. So if you look at the thickest of ice layers, we can see that it has got more than 6 dB higher gain compared to only a 4 millimeter ice layer, and that's with only 5.8 millimeter change in the thickness of ice. We can also see that because there's more ice, the antenna matching is improved, it takes longer to melt, and that means the tag can be read for a longer time. And at the end of this graph, this is where the tag stops being read by the reader due to the water, completely detuning the antenna and the received power being lower than the turn-on threshold or the sensitivity of the commercial IC we're using. If you want to improve the reading time or the reading range, then we need a higher sensitivity IC, or we can also resort to a higher gain antenna like a microstrip patch antenna or a more directional Yagi-Uda antenna or similar, which will improve the gain in the main lobe of the antenna. So can we use this to measure thickness? So we've taken the same values and we have observed a relation with varying thickness. We'll measure the thickness of the ice layer and we'll measure the signal strength. And we found that with a simple first order polynomial, we can actually fit the data with a very high accuracy with an R squared of more than 99.994. And we can see that this is valid from no ice, 0 millimeter thickness, all the way up to a 10 millimeter ice layer. And we'll be looking in our future work at how we can increase the thickness further and how sensitivity behaves. And that shows that RFID tags can also be used as ice thickness monitors and potentially to also inform us about the condition of the ice. The measured RSS also approaches the simulated and analytical superstrate variations. So when we calculate the gain changes along with the free space path loss model, we find that the values are in sync and there is still the same trend with distance and also with the gain changes, which shows that the behavior can be predicted and it can be coupled with calculations in order to obtain an accurate modeling of the environment the tag is operating in. So what other antenna designs are possible? Can we improve the design? And the answer is yes. One other design which we have considered is a printed loop antenna design. Again, we're looking at polymerized substrates. We're looking at a flexible and very low cost construction. And we can see that the gain change is very similar to the RFID dipole. In the graph, we've got a time varying relation between the RSS, in this case measured using a VNA because we've got a 2-port 50 ohm setup rather than an RFID setup. And you can see that when we start with the unloaded tag, our RSS is around minus 55. And as we add water, the RSS drops below a threshold. And that's the original threshold after buildup of ice. And then as soon as this water layer freezes, because the experiment is taking place in an environmental chamber below minus 10 degrees, you can see the signal strength rapidly improves, and it also improves well above the detection threshold around minus 55. We add further water droplets to investigate the effect of more noise, and as you would expect, it again degrades the gain significantly, so it falls below the detection threshold. However, as soon as the water freezes, which is what would happen in a real world case in a climate where we do expect ice to build up, the signal strength improves even further, and it shows that we can indeed measure the thickness of ice based on the signal strength. We introduced shadowing, so we've got human shadowing, and we can see that even though the moving average drops, it's still significantly above the detection threshold, and as soon as the shadowing moved away, we can get our magnitude back, so we get our thickness measurement back, and at all times the presence of ice is satisfied and the sensor will report an accurate ice measurement on the presence of ice. In our recent paper, we have presented, or in our recent preprint, we have presented a complete methodology for designing antenna-based sensors, which can apply to basically any external permittivity or any external sensor, be it ice or be it another material, and you'll find information where we compare this loop antenna to a dipole antenna. And we explain why the sensing performance is different and how to improve sensitivity. How does this translate to accuracy? So we have measured ice of different thicknesses from 0 to 5 centimeters thick. And we can see that the measured thickness using our RF signal strength closely approaches the measured thickness of the ice with an error margin less than 20%. So an error of 20% when characterizing ice thickness, that is better than radars, which are widely used in environmental sensing, especially that we're looking at very thin sheets which would otherwise be impossible to detect and are widely found in the smart cities or industrial applications. And we believe that this accuracy is mostly due to the accurate simulation of the antennas and due to the following the design methodology, which we have proposed in our preprint, which is currently available online. So to summarize my talk and our contributions, we find that antennas can detect low dielectric stimulants in the near field. They're very sensitive to even dielectrics, which are very low and are described as transparent to microwaves. We can see that ice can be detected by positive gain modulation, where we increase the RSS to improve immunity to interference, and we do this by doing impedance changes which modulates the realized gain of the antenna. The proposed sensor is a compact dipole antenna. It's matched to an RFID tag, and it can be read over a long range, over up to 10 meters, and its response is improved to stimulant. And we have also looked into different antenna designs with 50 ohm impedance, which can achieve the same and also have very high accuracy. So thank you for listening, and I look forward to hearing your questions.